Hi, everyone. We are now finished with the electricity and magnetism part of the class. So the last couple of weeks, we will be dealing with thermodynamics, which happens to talk about temperature, heat, things like that. So the first chapter that we're going to for this is chapter 18. Then we'll look at chapter 19. So we're going to start chapter 18 today by talking about temperature. And so temperature is defined, or we can actually use many different thermometers, and we can define different temperature scales like Celsius and Fahrenheit. All temperature is based on the physical change of something that happens as heat is added or subtracted. So for example, water is how we define the Celsius scale, right? 0 degrees Celsius is the freezing point of water. 100 degrees Celsius is the boiling point. But in order to have kind of a more or uniform or constant temperature scale, people have in the past used what's called the constant volume gas thermometer. And that's what I'm going to talk about now. First of all, in order to describe it, I need to define something called pressure. Pressure is the force per unit area. So what I mean here is, let's say you have a gas in a container. And in this container, we have a little tube. So the gas actually goes down to the point right here. It's going to exert a force if you try to hold it there. If you put a surface there, it'll put a force on it. It's like the air in a tire puts a force on the walls of the tire. The force divided by that area that it's pressing against is what we call pressure. Now, things about gases also depend on the volume of the gas. So as we'll find when we talk about gases and things like that, we'll talk in terms of three variables often: pressure, temperature, and volume. We'll also talk about heat and define that, but basically what we're going to talk about with respect to the constant volume gas thermometer is that by adding heat, we're going to increase the temperature. And we want to use this as a thermometer to set up a temperature scale, right? So one thing you might do is put the gas in boiling water. Well, then you know it's 100 degrees Celsius, right? And comparing to your Celsius scale. Put it in freezing water, ice water, you know it's 0. But either way, what we are going to do is by adding heat or subtracting heat, we are going to change the temperature of the gas. Now, generally speaking, what will happen is the pressure will increase over here. We want to keep the volume constant by keeping this line right here the same place. So what you could do is, for example, put a liquid like mercury on top. Now, as the temperature gets hotter, the temperature goes up, you need to add more liquid liquid mercury to increase the pressure that's pushing down and keeps everything balanced at the same point. Right, so that you keep the volume constant. Now, as it turns out, we didn't study fluids so far in this class, but the pressure depends on the height of the column of mercury, for example, that you put here. Or you could, measure pressure some other way. But basically, what you get is as the temperature goes up, the pressure increases, and what you could do is plot a graph of pressure versus the temperature. Now the pressure, I should say, is in units of newtons per meter squared, which is the metric system, and we call this a Pascal. So 1 Newton per meter squared is a Pascal. But what you'll find is you'll get a pressure over here at a temperature, say 100 degrees, a pressure at 0, right? And you can get pressures all the way along, and you'll find that it is a straight line. And you can even go below freezing, get down, 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 and right, eventually you're going to come to a point, you just can't get a lower pressure. Maybe you can get extremely low, but you can't get to 0 pressure. Right? Now pressure is caused by the motion of the atoms, so to get 0 pressure you'd have to completely stop them. But what you can do is you see this as a straight line and you can extrapolate it back. And you can do this for different gases. Maybe this is hydrogen gas. Now you might do nitrogen and you might get a different slope, right? A different straight line for nitrogen. But what happens is if you extrapolate it back for any of these gases, you come to zero pressure at about 273.15 degrees negative Celsius, right? So negative 273.15. So that point we call absolute zero, right? You can't get any lower temperature than that. You've stopped all of the atoms from moving. There's zero pressure. And this is our defining point for the Kelvin temperature scale. So the Kelvin temperature scale is related to Celsius just by adding that 273.15, right? So the Celsius scale and the Kelvin scale are very similar. They just have different zero points. The Kelvin scale starts at negative 273.15, right? Water freezes at 273.15 Kelvin and boils at 373.15 Kelvin. And notice we don't say degrees Kelvin, we just say Kelvin. That's the temperature that we have. Of course, the other scale that's commonly used in the United States is Fahrenheit. Fahrenheit uses different divisions. Kelvin and Celsius have the same divisions between each, right? Going from 0 to 1 is the same amount. The Fahrenheit scale has different divisions. Freezing's at 32 degrees Fahrenheit, boiling water's at 212. So we have to get this formula to relate Fahrenheit and Celsius. Sometimes you might have to convert between those three temperature scales. Now I said that you can use anything that changes with temperature as a thermometer. Some examples of that are the resistance of certain metals or wires. Another thing that happens as you change the temperature of a metal, right, is expansion. So let's say you have a railroad tie or a long piece of metal. If you heat it up, it will get longer, right? So it will start at an original length, L0, and it'll change by an amount delta L as you go from a temperature 1 to a temperature 2. Right? Now delta T, the change in temperature, is T2 minus T1. This law that I'm going to write down is the first of kind of a number of empirical or experimental laws that we'll see in thermodynamics. These laws you can understand if you think in terms of atoms, but it takes a lot of work to derive this expression. And this law kind of comes from just doing experiments and seeing, oh, okay, this metal expands by this much if I change the temperature by 10 degrees Kelvin, and so on. But generally speaking, the change in length that you get, delta L, is proportional to the original length, L0, and a constant that depends on the type of metal or material you have, alpha. Alpha is what we call the coefficient of linear expansion. And then it's also proportional to delta T, right? The bigger delta T temperature changes, the bigger the expansion will take place. This formula you may use in one of the problems. Now, you can also have, generally speaking, right, an object that has a whole volume like a sphere or a cube of metal. And as you increase the temperature, you get a volume expansion. You get a change in the volume that's proportional to the original volume, V0, and the change in temperature. And then you have a volume coefficient of expansion, which a lot of times is just 3 times alpha, 3 times the linear expansion coefficient. All right, so this is the first of our properties that depends on temperature. And again, these are kind of empirical relations. You can get them by doing experiments and kind of get this relation from the experimental data. So I'm going to stop there for this part. We'll go into the definition of heat in the next lecture.